Welcome everybody to Scale Models. I said I was going to do this before the video and I didn't. Silly. I knew that was going to happen. Lesson number 4. So up until this point, we've looked at linear scale factor, and then last lesson we looked at area scale factor. Today we're going to move into surface area and volume scale factor. And see how they relate to the linear scale factor. Basically, we're trying to find a relationship between all of the types of scale factors because things change at a different rate. If I double the dimensions of a rectangle, for example, if I double the length and double the width, we know that the area is going to increase by a factor of 4 because doubling is 2 and 2 squared is 4. So anyways, that's what we learned last time. Let's dive in. We've got more of these charts, and these charts are, I know they're maybe a little bit annoying for you, or maybe you don't like the way they're presented, but they are a good way for me to see that you know how to do some of this stuff. So you probably will see something like this on a test. So what we're going to do is look at surface area of rectangular prisms, I believe. Yeah, 3 by 5 by 1. So let's just go through the first one together. So we have a 3 by 5 by 1 rectangular prism. So what that's going to look like is something like this, where we have a 3 by 5 by 1, and we want to calculate the surface area. Surface area is a really, really annoying formula, and I'm not going to ask you to calculate it very often. So I'm going to move through this first chart pretty quickly. So just as a reminder, the surface area is all of the areas of this three-dimensional shape. So we want to calculate the area of this, the area of that, the area of this, and then the three sides that we can't see on the back. So what we're going to do, I mean, the surface area formula is something like 2 times the length times the width plus 2 times the length times the height plus 2 times the width times the height. So it's just a pretty big formula. So the surface area of this original rectangular prism is 46 centimeters squared. It's still an area, so it's still centimeters squared. Now, if we apply a linear scale factor of 2 to every dimension, you can see that 3 times 2 gives us 6, 5 times 2 gives us 10, and 1 times 2 gives us 2. And we can put these new dimensions, this is a length, a width, and a height, a length, a width, and a height. We can put these new dimensions into our surface area formula, and we get our new surface area of 184. So we've created a scale rectangular prism. It's bigger because our scale factor was bigger than 1, and we have a surface area of 184 centimeters squared. So we can look at the surface area scale factor if we do new surface area divided by our original surface area. So our new surface area was 184, our original surface area was 46, and we can reduce that to be 4/1 or just 4. And you know what? That's the only one I'm going to do for this chart because it's just pretty repetitive from the last video. Because it's an area, so surface area is a 2-dimensional measurement. It's still an area, right? So that means the surface area scale factor is going to equal the linear scale factor squared. So just because it's a surface area doesn't mean it's going to change anything. It's still area. So it has the same relationship as a regular area scale factor. And we know that means also that the square root of the surface area scale factor is equal to the linear scale factor. So it's the same as the area from last notes, L3. What I really want to get onto is the volume. So we're going to look for a relationship between linear scale factor and volume scale factor. So just as a reminder, volume of a rectangular prism is length times width times height. and the volume is how much space that takes up. So if I have a 3 by 5 by 1, like I drew above, 3 by 5 by 1, it's not the measure of the areas of everything, it's how much space this entire shape takes up. So what we do is we go, well, 3 times 5 times 1, and our original volume is 15, and it's in centimeters cubed because it's going to be centimeters times centimeters times centimeters, so 3 centimeters. And we know volume is three-dimensional, right? Volume is a 3D measurement. It's how much space it takes up. So now what I'm going to do, or what they did here, is they're going to apply a linear scale factor of 2. So that means it's going to change any linear measurement by 2. So this length and width and height, they're all individually one dimension. So we are going to multiply all of them by 2 to get our new dimensions of a 6 by 10 by 12 rectangular prism. And we can say, well, the volume is going to be length times width times height. So we can go 6 times 10, which is 60, multiplied by 2, which is 120 centimeters cubed. So now we have a new volume, we have an original volume, and we can find the volume scale factor. So we're going to do new volume divided by original volume. So 120 divided by 15, and we can reduce that to be 8 over 1 or just 8. So far we have a linear scale factor and a volume scale factor. Linear scale factor of 2, volume scale factor of 8. Let's do one more, or maybe 2 more. So we have a new rectangular prism. It's a 9 by 6 by 12. This is rectangular prism B. So the volume is going to be 9 times 6 times 12, and that's going to be 648. Make sure you use your calculator for those. So our volume is 648 cubic centimeters, or centimeters cubed. And what we're going to do is apply a linear scale factor. Be careful. A linear scale factor of 1/6. So what you want to do is multiply all of your dimensions by 1/6. 9 multiplied by 1/6, 6 multiplied by 1/6, and 12 multiplied by 1/6. And what you're going to get is, well, 9 multiplied by 1/6 is 1.5, 6 multiplied by 1/6 is 1, and 12 multiplied by 1/6 is 2. So our new rectangular prism is going to be a 1.5 by a 1 by a 2. Hopefully that makes sense. We're just changing the length, the width, and the height. And now we can calculate volume, length times width times height, 1.5 times 1 times 2, and we get a volume of 3, which is just tiny, itty bitty. So we can find the volume scale factor by doing new volume, which is 3, over original volume, which is 648, and that reduces to 1 over 216. So I had a linear scale factor of 1 over 6 and a volume scale factor of 1 over 216. Let's do one more. We have a rectangular prism of 4 by 8 by 5. So if we multiplied all of those together to get our volume, length times width times height, we get 160 centimeters cubed. And now we want to convert each of our measurements by a linear scale factor of 3 over 2. So 4 multiplied by 3 over 2, and that gives us 6 by 8 multiplied by 3 over 2, and that gives us 12 by 5 multiplied by 3 over 2, and that gives us 7.5, good old decimal. So now our new rectangular prism is a 6 by 12 by 7.5. It's a little bit bigger, which is what we expected because our linear scale factor was larger than 1. So the new volume from our new dimensions, 6 times 12 times 7.5, are going to give us 540 centimeters cubed. New volume divided by original volume, you know the drill. 540 divided by 160, and we can reduce that to be 27 over 8. So our last one here was our linear scale factor of 3 over 2, and we have a volume scale factor of 27 over 8. So how do we relate linear scale factor and volume scale factor? That's the whole point of this exercise. So last time, when we went from a one-dimensional measurement, this is 1D and this is 3D. So last time we were looking at the relationship between linear and area, and that was 1D to 2D, and we squared things. This time we're going 1D to 3D, so let's cube it. 2 to the power of 3 is going to be 8. If we cube that whole fraction, it's like saying 1 cubed multiplied by 6 cubed. So 1 cubed is 1 times 1 times 1. 1 multiplied by itself 3 times, and that's going to give us 1. 6 cubed is 6 times 6 times 6, and that gives us 216. 3 cubed is 27. 2 cubed is 8. So if we're going from 1 dimension to 3 dimensions, the scale factor is cubed. So you can see right here we have volume scale factor is equal to linear scale factor cubed. Or we can go the opposite way and say the cubed root of volume scale factor is equal to linear scale factor. Hopefully that makes sense. So on the next page, you've got this awesome summary sheet. So it gives you a little bit on linear scale factor, and we know that the formula is nu over original. Then it talks a little bit about perimeter scale factor, which is equal to, this is the important bit, the linear scale factor. It's the same thing, right? Because perimeter is a linear or one-dimensional measurement. Then we moved into area scale factor, and we know that area scale factor is linear scale factor squared, because now we've moved into a two-dimensional measurement. And then we looked at surface area scale factor very briefly, because it's actually the same thing as area scale factor. So again, we're in a two-dimensional measurement. And last but not least, we looked at volume scale factor, which is the volume scale factor is the linear scale factor cubed, because we are in a 3D, a three-dimensional measurement now. And it gives you a nice little summary down here as well. So you are going to have this on your test, so it's good to read it over and know where all the information is. It should give you enough, I think, to really feel comfortable with all of this. It is a lot trying to like work through 1 dimensions, 2 dimensions, and 3 dimensions, but with this little summary sheet, it should help quite a bit. So we are going to skip the next page, because I don't actually have it, and I also don't really want to bog you down with the square cube law too much. I feel like we're just going to be doing the important bits, and I don't think that one's super important. So here it says a globe company produces globes with a diameter of 30 centimeters. So that means, just so that you remember, a diameter, if this is a sphere, the diameter is the measure across through the center across the entire sphere or ball. So that's a diameter, and then a radius is just from the center to the surface, so half of the diameter. So they construct globes with a diameter of 30 centimeters. Isabel, the manager, is having her employees construct a globe with a diameter of 1.5 meters to put on the roof of their building. So it's much bigger. The surface area and volume calculations of the globes with the diameter 30 centimeters are shown below. Complete the work below to calculate the surface area and the volume of the globe of with a diameter of 1.5. So we're going to calculate the surface area of the big one and the surface area and the volume of the big one. So the first thing I want to talk about is, well, we know our diameter is 1.5 meters, but we want everything in centimeters. So let's quickly just switch that into centimeters. So if 1 meter is 100 centimeters. 1.5 meters is 150 centimeters, right? So that's 150 centimeters. They give you the formulas here. So surface area of a sphere is 4 pi times the radius squared, and volume is 4/3 pi times the radius cubed. So if the diameter is 150 centimeters, the radius is half of that, and they actually gave it to you right here. The radius is 75 centimeters. So now we just need to plug things into the formula. So the surface area is going to be 4 times pi times our radius squared, which is not 0.75, 75. It looks like there's a point there. I apologize. I'll try to erase it. It didn't work. 75 squared. We can type that into our calculator, making sure that we put those brackets in around that 75, and we will get, oh good, I don't have the answer key. Let me pull up my handy dandy phone calculator because that's all I've got with me. Sorry, everybody, I wasn't prepared. 4 multiplied by pi. I think phone calculators are not reliable, but I think it's 70,685 centimeters squared. Let's do the volume now. I'm going to run over and get my calculator quick because I won't be able to do that one. Okay, I got my calculator. No fears. Volume is 4/3 pi times our radius cubed. Our radius is 75. So it's going to be a very large number. 4/3 multiplied by pi multiplied by 75 cubed. So it looks like it's in the millions, 1,700,067 and 145 centimeters cubed. So the biggest thing I wanted to talk about is the next part of this question. So it says use the above results to determine to the nearest whole number the following scale factors from the 30 centimeter globe to the 1.5 meter globe. So we know scale factor is, it's new over original. So we can do that for every one of these, right? So we are going to do, for linear, we can use the radius. For surface area, well, we calculated the surface areas. And for volume, we're going to use volume. So scale factor is going to be the new radius, which was 75, over the old radius, which was 15. And what do we get? 75 divided by 15 gives us 5, right? Our scale factor is 5. The surface area scale factor is going to be our new surface area, which is 70,685 divided by our original scale, our surface area, 2,827.4. And that would give us 7685 divided by 2,827.4. That gives us 25. And then volume scale factor is going to be our new volume, which is 1,767,145 over our original volume, which is right here, 14,137.2. And if I type that into my calculator, I get 125. So I just want to show you the link between all of those, right? The relationship. We know that our linear scale factor was 5. And we know that surface area scale factor is the linear scale factor squared. So we could have just done, well, 5 squared is 25. And we know the volume scale factor is just equal to the linear scale factor cubed. This is all from your summary sheet. So we could have taken our linear scale factor and cubed it, and it would have given us 125. So either way you want to do that, you can. I mean, you could have just done the whole calculation every time, but we could have figured out the volume scale factor without actually having to do this big calculation up here to find the new volume. We could have just taken the linear scale factor and converted it into a volume scale factor. Hopefully that all makes sense. I'm going to stop it right there. Thanks for watching. Don't forget to like and subscribe.